I'm Dr. Kailas Mali, and in this session we'll discuss the remaining physicochemical properties of the drug which are going to affect the oral absorption. Learning objectives. You will able to understand effect of particle size on drug absorption. You will able to explain the effect of salt form of drug on absorption, and you will able to describe the pH partition hypothesis. So let us see how the particle size is going to affect the oral absorption. Particle size and effective surface area or surface area are inversely related to each other. The surface area, it is divided into absolute surface area and effective surface area. So what is absolute surface area? Absolute surface area, which is the total surface area of any particle, while the effective surface area, which is the area of solid surface exposed to the dissolution medium. Effective surface area, it is directly related to dissolution rate. The area, it is exposed to the dissolution medium. So greater the effective surface area, more intimate the contact between the solid surface and the aqueous solvent, and faster the dissolution. Micronization, it is the one of the approach by which we can convert the absolute surface area into the effective surface area by reducing the particle size. For example, micronized product of ondansetron shows greater dissolution rate than the unmicronized ondansetron. The other examples are like the griseofulvin. Sometimes the micronized product may get float on the surface. There might be chances of aggregation of the particle, thereby converting it into the larger particle size, or sometimes there may be the settling of the particle which will prevent the dissolution rate in the case of hydrophobic drug. So in these cases there is a need to use the wetting agents or the surface active agents which will improve the wetting of the particle, which will prevent the floating of the particle and increases the dissolution rate. So this is about the particle size and effective surface area. Salt form of the drug. More than 60% of drugs are available as weak acids or weak bases. When we are converting these weak acids or weak bases into the salt form, there is a drastic improvement in the dissolution rate. Generally, weakly acidic drugs forms the salt with a strong base like sodium or potassium. For example, the barbiturates like phenobarbital sodium and sulfonamide. Whereas the weakly basic drugs forms the salt with the strong acid like hydrochloride or sulfate salts. For example, alkaloids, say the propane alkaloid, atropine sulfate. So in all, converting the weak acids or weak bases into its salt form improves the solubility and the dissolution rate, and thereby the drug absorption. Let us see how it improves the dissolution or the solubility. Look at the figure. When the salt of weak acid it is prepared with a strong base and kept into the bulk of solution, there is a formation of a stagnant layer. The formed stagnant layer, it is having the pH which is near to 6 to 5, and the bulk of solution, it is having the pH which is relatively low. Say for example, gastric juice, it is 1 to 3. So from the diffusion layer, the drug is going to be dissolved in a soluble form, or it might get precipitated into the fine particle. From the soluble form of drug, it is going to be absorbed through the gastrointestinal barrier into the systemic circulation. While the precipitate, if the precipitate is formed, it is having a very small particle size from which the drug is going to be dissolved into the gastrointestinal fluid, and furthermore it is going to be absorbed into the systemic circulation. So this is the way by which there is a improvement in the dissolution of a drug when it is converted into the salt form. Moving towards one of the important aspects, that is the pH partition hypothesis. Here we are correlating the dissociation constant and gastrointestinal pH. Brody et al. Explain the pH partition hypothesis, and same we are using to understand the effect of pH on the dissolution and the absorption. So theory states that for the drug compounds molecular weight greater than 100 Dalton, primarily transported across the biomembrane by passive diffusion, and the process of absorption is governed by the pK of drug, lipid solubility of unionized drug, pH at absorption site. So these are the three parameters which governs the passive diffusion process. So as we know, the most of drugs are weak electrolytes, either they are weak acids or the weak bases, and the ionization of these drugs depend on the pH of biological fluid. As the gastric pH, it is around less than 2, while the intestinal pH, which is ranging between 5 to 8.2. Only the unionized drug with a sufficient lipid solubility can cross the barrier until the equilibrium is attained. According to pH partition hypothesis, only unionized drug is having the ability to cross the barrier, and it should be the lipid soluble. The absorption is governed by absorption. The drug is going to be absorbed by the passive diffusion process. So it is based on certain assumptions like gastrointestinal tract. It is a simple lipoidal barrier. Larger the fraction of unionized drug, faster the absorption. Greater the partition coefficient of unionized drug, there will be the better absorption. Let us move towards the drug pKa and gastrointestinal pH. So unionized fraction, it is a function of pK of drug and pH of gastrointestinal fluid, because the acidic drugs are ionized into the basic pH, whereas the basic drugs gets ionized at an acidic pH. Low pK of acidic drug, in a strong acid there will be the greater ionization. So these are the strong acids if the drug is having a low pK. If the basic drug it is having a high pK, all these are the strong bases and they are ionized at all pH range from 1 to 12. Let us move towards to understand these concepts by using Henderson-Hasselbalch equation. So, according to Henderson-Hasselbalch equation, for acids, pH is equal to pK plus log ionized drug divided by unionized drug. For weak acids, pH is equal to pK plus log unionized drug divided by ionized drug. So with the help of these equations, it is possible to get idea about the ionization of acidic drugs as well as the basic drugs. It is possible to make certain generalizations with the help of pH partition hypothesis, how the drugs are going to be absorbed into the systemic circulation. As the acids are divided into very weak acids and strong acids, while bases are divided into very weak bases, moderate bases and strong bases. Let us see the certain generalizations regarding ionization and absorption of acids. For example, very weak acids with a pK greater than 8. So all these very weak acids, for example, pentobarbital, hexobarbital, phenytoin, ethosuximide, these are unionized. Maximum amount of drug it is unionized at all pH values, and the absorption is rapid and independent of gastrointestinal pH. It indicates that very weak acids are well absorbed throughout GIT. In case of moderately weak acids with a pK 2.5 to 7.5 like cloxacillin, aspirin, ibuprofen and phenylbutazone, absorption is pH dependent and they are present in an unionized form at an acidic pH and hence absorbed well in an acidic environment at an acidic pH. In the case of strong acids with a pK less than 2.5, they are ionized at an entire pH range of gastrointestinal tract and poorly absorbed from GIT. For example, disodium chromoglycate. So now it is possible to understand how the acidic drugs are going to be absorbed from the gastrointestinal tract. So in short, very weak acids, the absorption is pH independent. Strong acids, they are ionized at all entire pH range and poorly absorbed, while moderately weak acids, these are its absorption is pH dependent. Moving towards the certain generalizations regarding ionization and absorption of bases. Very weak bases with pK less than 5. These are present in an unionized form at all pH values and absorption is rapid and independent of gastrointestinal pH. For example, theophylline, caffeine, oxazepam, diazepam and nitrazepam. Moderately weak bases with pK 5 to 11, absorption is pH dependent and it is better absorbed from alkaline pH. For example, morphine, chloroquine, imipramine, amitriptyline. Strong bases with pK 11, above 11, they are ionized at an entire pH range of GIT and poorly absorbed from the gastrointestinal tract. For example, guanethidine. So it indicates that The very weak acids, they are unionized at all pH values and absorbed from gastrointestinal tract well. While the strong bases with pK 11 or greater than 11, they are ionized in the entire pH range of GIT and poorly absorbed, while the absorption of moderately weak bases is pH dependent. Moving towards the aqueous solubility. So, what is the total aqueous solubility? That is ST. It is the sum of concentration of ionized and unionized drug in the solution. So total solubility of unionized form of drug is known as intrinsic solubility of drug. For acidic drugs, St is equal to Sa in bracket 1 plus 10 raised to pH minus pK, while for basic drugs, St is equal to Sb in bracket 1 plus 10 raised to pK minus pH. It is possible to make certain generalizations with respect to the total solubility and unionized fraction solubility. For example, related with the weakly acidic drugs, when the pH is greater than pK, St is very greater than Sa and ionization of drug increases. When the pH is equal to pK, St is equal to 2Sa and there will be the 50% ionization. When pH is less than pK, St is equal to Sa and almost the drug exists as a unionized form. In the case of basic drugs, when pH is greater than pK, St is equal to Sb and drug exists as unionized form. When pH is equal to pK, St is equal to 2Sb and there will be the 50% of ionization. When pH is less than pK, St, that is total solubility, it is greater than the unionized form solubility and ionization of drug increases. Moving towards the lipophilicity and drug absorption, we know that there should be the drug have certain hydrophilicity as well as the lipophilicity, so as to it is going to be absorbed into the systemic circulation. Hydrophilicity it is required to dissolve into the gastrointestinal fluid, while lipophilicity is required for the permeation of drug through the biological membrane. So if the drug is having a hydrophilic lipophilic balance, we'll get the optimum absorption. The partition coefficient is the indicator for the lipophilicity of the drug. So we are getting the rapid rate of absorption when the partition coefficient values lies between 0.12 to 100. For example, thiopental, phenylbutazone, benzoic acid and salicylic acid. Almost they show 50 to 70% of absorption. Moderate rate of absorption when these values lies between 0.002 to 0.03. For example, aspirin, theophylline or sulfanilamide, the values lies between 20 to 30%. Values for the absorption lies between 20 to 30%. And slow rate of absorption when the partition coefficient it is less than 0.02 and very less amount of drug is going to be absorbed, that is less than 5%. For example, barbituric acid or the sulfaconidine. So this is about the lipophilicity and drug absorption. So drug should have the optimum lipophilicity as well as it should have the optimum hydrophilic character, so as to it is going to be absorbed well into the systemic circulation. Let us move towards the limitations of pH partition hypothesis. There are four limitations, that is presence of virtual membrane pH, absorption of ionized drug, influence of surface area and residence time of drug, and presence of aqueous unstirred layer. That is the very first one, presence of virtual membrane pH. For acidic drug, the curve gets shifted to the right side, while for basic drugs, curve gets shifted towards the left side. It indicates that there is a presence of virtual membrane pH which is different than the luminal pH. So this is the first limitation of pH partition. Second limitation, that is the absorption of ionized drug. As we have seen in the pH absorption curve, there is a shifting of the curves from left to right and right to left. Then the certain ionic drugs are going to be absorbed, maybe by other mechanisms like ion pair transport. There are also the large lipophilic groups are present onto the drug, which is responsible for the absorption of a drug. So the next parameter, that is influence of surface area and residence time. As we know that the acidic drugs are well absorbed into the stomach and basic drugs are well absorbed into the intestine. The surface area for the stomach, it is very less. Also the residence time, it is very less in contrast to intestine. In the intestine, the drug stays more time, and also the presence of villi and microvilli, which increases the area available for the absorption. So both the acidic drugs as well as the basic drugs are well absorbed into the intestine due to the long residence time and the greater the surface area available for the absorption. Presence of aqueous unstirred diffusion layer. As we have seen that in the generalization assumptions, the gastrointestinal barrier, it is a simple lipoidal barrier, but actually on the barrier there is a presence of aqueous unstirred layer, and the drug should have the sufficient solubility into this aqueous unstirred layer. So these are the four limitations of the pH partition hypothesis. Moving towards the drug permeability and absorption. So absorption is expressed by the M, effective permeability, area, then apparent concentration into the residence time. There are three properties, major properties, which determines the permeability of drug. That is the lipophilicity, polarity of the drug, and the molecular size. Moving towards the drug stability, as we know that during the storage period there might be chances of degradation of the API, and the second thing, that is destabilization of drug in the GIT, which alters the dissolution as well as the absorption. And the very last point, that is stereochemical nature of the drug, which also affects the absorption. So in this session we have discussed the surface area, particle size, then salt form of the drug, then the effect of pH on the absorption, then the dissociation constant, lipophilicity, drug stability, and stereochemical nature. So hope the session will be useful to you to understand how physicochemical factors are going to affect the oral drug absorption.